अब इसमें से बहुत कुछ कितने लोग हैं? 6 लोग हैं ना? में से तुम लोगों को कुछ याद है कि सब कुछ ही करूँगा? मैं सब कुछ करता हूँ, ऐसे डिस्कस टाइप करते जाएगी। तुमको जिधर भी प्रॉब्लम होगा बताना, ठीक है? मेरा थोड़ा रिवाइज हो जाए। ओके, सो माय टॉपिक इज simulating Hubbard model, exact diagonalization, and quantum computing. But the topic is this. But basically, what we are discussing, what we will discuss is quantum simulations. So, using quantum computing, how do we simulate quantum systems? Okay, so should I have put a layout for this? So, something about the model in general, Hubbard model. So, how do I start? यार लिखने का रहता तो सही रहता, कोई नहीं. Basically, any model, okay, any model of let's start with many body theory. Okay, we will start with many body theory. Generally, in many body theory, what we have is that we have a bunch of electrons and protons. Okay, if you take any object that is around us, it is made up of electrons and protons. And since the number is so large, it is impossible to deal with the dynamics of such a system. So when it is impossible, then what we can do is we will look at only the relevant scale. Now, what is a relevant scale? The relevant scale is at which we are going to perturb the system by experiments. So what we will do is if you take a metal, for example, metal is a very good example. If you take a metal, then it is bounded by electrons, protons. Okay, so it is a bound state of electrons and protons, and it has some bound state energies. Now, if you put an electric field, then the electrons which are loosely bound to the nucleus, which are called as free electrons, responsible for conduction, they activate. And if they activate, they go into higher energies, and thus we get what we call as conductor. So this is the relevant scale at which we do experimentation. We apply electric field and we see the response. We do not apply such a large electric field that the bound state is broken. We don't want to destroy the solid. We just want to perturb it and see what is the response so that we can know about the properties of the material. Now, it was very nice for the study of metals. Metals are very useful. Everything around us has metals. So we what we do is the theory of metals started with electrons which are almost free. They are not very tightly bound to the nucleus. So if they are free, they will have a wave function which is not localized. It is very delocalized, and therefore uh, we can use this as our basis states. So all of you know about basis states, so I don't need to go deep into that. But basically, we can use e raised to I car our plane waves as our basis states, and it can very well explain the conduction part. This is the very delocalized basis states. Okay. Uh, if you take the opposite spectrum, if you take the right side of the periodic table, we have we have electrons which are very tightly bound to the atom, to the nucleus of the atom. So as you know, they are called noble atoms, right? So on one side we have something which is very localized, electrons, and their wave function is very localized around that nucleus. And on the left side of the periodic table we have something where the electrons are very delocalized. So we called the left side ones the s orbital electrons, and the right ones, I don't know what they are called. They do lie in the p block of it, but they are tightly bound. In between, which is the d electrons, they lie somewhere in between. So they are neither very localized nor very delocalized. And if you take the wave function of an electron on an atom, it will overlap to the neighboring atom. Okay, so there is overlap between the wave functions. Now if there is a overlap between the wave function, then the electron can turn, or I should say that since there is a periodic potential, okay, and the periodic potential and the width of this potential is small enough, then we can see that the wave function, which is overlapping wave function, the the electron can tunnel through the uh, potential, periodic potential, and it can jump from one atom to another atom. Now if you see this Hamiltonian which I have written, basically it has two parts, the kinetic energy part and the potential energy part, but it is not the usual kinetic energy part. Usual kinetic energy is positive, right? But here you, as you can see, there is a minus sign. Why there is a minus sign? Because it is passing through one side to another. It is jumping from ith side to say I plus one side through tunneling, right? And if it is tunnel, this is not classical. The energy is negative. Okay, so that is why there is a negative kinetic energy. And the second term is the Coulomb repulsion term between two electrons on any two side. So in the general Hubbard model, this repulsion was for any side, but Hubbard realized that we will take the strongest contribution. What can be the strongest contribution is when two electrons are very near to each other. Where can be they be nearest to each other? If they lie on the same atom. So if they lie on the same atom, then we have this repulsion will activate or it will not. There is also extended Hubbard model in which the what we say repulsion is activated on the nearest neighbor. Even if they are nearest neighbor, they are close enough so that they feel this repulsion. Now from solid state physics, you can say that the first part of only kinetic energy is called the tight binding model. Okay, so the electrons are relatively tight binded, and the basis states are the localized states, and tight binding is the perturbation over the states. Okay, this is called tight binding model, and along if you add that, if you add the realistic Coulomb repulsion, then it is called Hubbard model. Okay, so this is the introduction to the model, and we will be using two parts so to solve this model. There are actually a couple of methods to solve this model, but there are I think four methods. The also okay, this I should mention that the analytically we can calculate only for one dimension. The method is called Bethe-Ansatz. Okay, Chaitan is there. So Bethe-Ansatz is the only analytical method we have to solve it, and it is not for general dimensions. In our general solid is 3D, but it is not possible to solve it using Bethe-Ansatz. And for 2D and 3D we don't have any analytical method. For 1D we can solve with Bethe-Ansatz. So for 2D and 3D what we do, we use numerics, and in numerics we have a couple of methods. So the most not how should I say, the most correct one, or the which gives perfect result is exact dilation, which I will show you. But it is restricted to the number of bits we can use, and the bits I'm talking about are classical bits. So we are limited. We have limited number of classical bits when we are doing it using exact dimension. But if you want to scale, if you want to do for large number of sites, then we have what is called DMRG, density matrix renormalization group. So people use DMRG for large number of sites because realistically, see, the dynamics of these systems should be done on large number of sites. Then they will be closer to the experimental stuff. And then another method we have is quantum Monte Carlo. People use quantum Monte Carlo. We know that there is a classical Monte Carlo, so there is a quantum Monte Carlo also. And as you can see, the newest method that we have is quantum computation, variational quantum isotope, which we will discuss here. I do not understand everything about it, but I wish to discuss what I do understand, and if possible get some inputs from you. So I have told about the model and the methods. I will change. So this was the basis state which I told you. They have a name. It's called Warnier wave functions. It looks very terrifying, but it's very simple actually. You can see here that this is a Fourier transform. This is nothing but a discrete Fourier transform. This first this wave function is Bloch wave functions. Okay, so we have Bloch wave functions. These are periodic wave functions. Okay, and from Bloch theorem we know that these are periodic, and you just take a discrete Fourier transform of this. So because they are periodic, and mathematically this is the function, right? So it is a periodic function, and it will have discrete k values. Why we will add discrete k values? Because we apply a periodic boundary condition. So they have discrete. There are large number of these, but still it is discrete. Now these discrete k values are periodic, and if you take a discrete Fourier transform, you will get this wave function. So we have changed the basis from Bloch states. We are going into discrete states. You can relate this using XRD. What we do in XRD, there is a periodic potential of atoms, right? And there are atomic densities at each site, and it is periodic. And we apply the electromagnetic field. Then electromagnetic field comes out, and we detect this. Now when we detect this, what we are detecting is the net electric field due to all the other atoms at different positions, right? So we get a peak. Now if you want to evaluate, you are actually, what you are doing is essentially going into the Bloch state, right? And you are testing at which k values will there be a peak. And if you are going into this space, which is also called reciprocal space, you can revert back, take a Fourier transform, and go into the real space. So this is our real space. So we are not doing anything exotic here. We are just changing the basis states. For those who know about second quantization, the field vector is just expanded in this discrete space. Instead of Bloch states, we are just using this discrete basis states. And you can see the label here is I. Here it is sum over k. So what is the, I think there is a typo here. No, good. So when you sum over k, what will are left with I? So I is our index. Similar to how we have, let's say the best example is our harmonic oscillator. Our harmonic oscillator is labeled by quantum numbers 1 2 3 4, right? Okay, so there our basis states are the Harmonic oscillator wave functions, and you can now label these electrons by using this ith site. So if two electrons are on the same site, they will have some energy. If they are on the different side, they will have a different energy. Okay, now uh, gamma is the band index, but what we are doing is only we are taking a single band. Okay, so Hubbard model is only for a single band, so it is tight binding but only single D band. Anything else? Okay, there is also a orthonormality. Similar to, we'll again take a harmonic oscillator example. If we have one number state and two number state, then they are orthonormal to each other, right? So if an electron is on ith site and another electron is on j sites, then they are orthonormal to each other. This is what is the orthonormality, and we'll use this notation. If one electron with up spin is on some side, it will be denoted by this, and down spin up and down. Okay. Now I will take two electrons example. This is exact declaration, okay? And this you can do it with hand itself. You can just take all the possible states, which are only which are only six. Okay, there is a typo here. They are six. I should have corrected this. So this is 0, up down 0, up down, and I think up down and down up. These are remaining. So we have these six possible states. So what is idea of exact diagonalization is, even if you want to do with hand, you take any of these states, you apply Hubbard Hamiltonian on this state. Okay. So when you apply, then both these kinetic energy operators and Coulomb energy operator will be operated on these states. Okay. So if you apply this H, what will happen in general? It will go into a linear combination of other states in general. So here I have written what might happen. So if this is up, then it is 0. You can simply see that if the first electron, if you apply a kinetic energy operator, it will jump to this operator, but because of the Pauli exclusion principle, this is not possible. So the kinetic energy term is 0. If you look at the potential energy term, no two electrons are on the same site, right? So the second term will not be activated. So it is 0. On the other hand, if you have these two electrons on the second site, same site, and if you apply the kinetic energy operator, you can see one has jumped from here. So we have got this state. From this state we went to this state, and we took a jump, and hence there is a minus sign. Okay, now this electron can also jump, so we have two terms, right? Also on the same site there are two electrons, so we do have this contribution from the U term. Now we have this bunch of operations. Now if you want to build a matrix, which is the Hubbard model matrix, right? So what you do is simply take another set of these basis states and you apply on this on the right hand side, and if you apply on the right hand side, then what we can get is the whole matrix. You can develop the whole matrix. So, and you simply what you use orthonormality to build this. So here is the matrix. Now if you want to do it with exact diagonalization, you simply what is you have this matrix and we need to diagonalize it. So using any package, standard package, we can diagonalize this and get the ground state energy. This is how exact diagonalization works. Now because the as you increase the number of electrons or sites, the matrix size increases very fast, and the classical qubits are not able to handle this. So if you store the basis states as our usual classical bits, then you have very limited computation power. So that is why you can calculate energy for only very small number of cells. So our future superficial idea is that using quantum computing, we might be able to do this for a very large number of sites. So what is quantum computing? I won't go into quantum computing so much. I want to focus on quantum simulation, and that is why uh, I will tell you what is needed, uh, what is the minimum number of stuff. So first we need to know that these are quantum bits. Classical bits which we had in our usual computer, they can only take 0 and 1 values. But this is a quantum bit, and a quantum bit, why there is a special name? Because in general, if you take in general, qubits is name given to anything which can represent this superposition. Now if you take any two quantum bit system, like a photon, right? A photon can have two polarizations, but there can also be a linear superposition of a photon. So if you want to use you can use photon as qubits. So that is why qubits is a good general one. Any two level systems you can use. So if you have a general two level system, we can represent a qubit using this. So now what we want to do is also uh, a better representation is what we called as, this is called a Bloch representation. Okay. Now in this Bloch representation, what we do is spin is a very good example. So spin is the general qubit that I will take as example. So if you take a spin, 3D spin, so it has x, y, z components, right? So a single spin has what, 3 degrees of freedom, right? In polar coordinates are theta phi, right? But but there is a condition. There is a condition that this spin, the radius of this spin will not change. And how do you put it mathematically? So alpha square plus beta square should be 1. That is the condition. So if alpha square beta square is 1, then we have only 2 degrees of freedom. It is theta and phi. So this is the idea of this representation, that we have only 2 degrees of freedom, theta and phi. Okay. So any state, any general linear combination of that spin can be denoted by only 2 sets of numbers, that is theta and phi. So if you take 0 in this, so the 0 state, that is the eigenstate of z, which is the 0 state, it will be noted in the north pole. And if you take 1 state, which is the eigenstate of z, another eigenstates, it will be denoted by 1, which is the south pole. Okay. Now eigenstate of y can be this, right? So it is a bit unusual, but it is very convenient to represent it. So we'll move. So this is very important. Now this is what quantum simulation is all about. It is the quantum mechanics at very core, how to do I imagine it like doing an experiment with quantum mechanics. So what we do is take psi. Okay, it is in a linear combinations of zeros and one in general. Now it is in this state, right? And in general there is always a Hamiltonian. Okay. And you want to measure the energy of that state कि अभी energy क्या है. So what you do is you apply that. In this case the Hamiltonian is only the single z orbit, so you sandwich this state between those two. So analytically what you should get, we should get very easy. We should get mod c0 square minus mod c1 square. If c1 if you had put this in equal superposition 1 by root 2, then analytically we expect that the probability is equal of being in the both state, and the expectation value is 0. So if you take large sets of measurements, then you should get the 0. Now this you can do it in a quantum computer. So you go into this into the Qiskit website, and you can use a simulator, right? So you set up your initial state as this, okay, and how you set up I will tell you. You can use I have not gone to I have not prepared special slides for that. I should do it, but the idea is very easy, that you apply a gate, what is called a gate. I did not tell about gates, right? So I should tell about gates also. You have this qubit, and it is in some state, right? Psi states. So there will be a spin, a real spin in the quantum computer, and if you want to change the state, then you will apply a magnetic field experimentally, and you can change the state and go to some other states, right? Now why this is a good representation, this Bloch sphere? Because what you do is you are essentially traveling on this. So using magnetic field you can go from here to here, so you can go to a linear superposition state. Okay, now how do you know that you are in these states, right? This is done by using measurement. We want to know these coefficients, right? So you can initially prepare them in z eigenstates by applying the magnetic field. Then you can change the magnetic field, you go into superposition, and you do repetitive measurements by being in this state. When you do repeated measurements, then you will get, it is like tossing coin. You are tossing coins, and you are tossing again and again and again and again, and as you see, you will get, if you do 100 coins, then 50% of the time you will get heads, 50% of the time, not exact 50, then it will be closer. So in an ideal quantum computer it should go to 0, but we have noise and everything else. Noise is a very different issue. I will tell you what. So this is what we do in quantum simulations. We prepare the initial state, then we prepare the Hamiltonian, right? And we do measurements experimentally, and then you get this expectation value. So you are calculating energy of the system, but experimentally. Now what is Jordan-Wigner transformation? You can see earlier I had used only one spin, right? And I had used only one qubit, I should say, and that one qubit I had prepared this. The Hamiltonian was only Z. In general, what will happen is you will have the Hubbard Hamiltonian, which is this, right? Now this is in discrete space, discrete I space. We want to use qubits to represent this Hamiltonian. How you can do that is you can use for one site you use one qubit. For one site you use two qubits, one for the upspin and one for the downspin. Okay. So if there is a electron, then that qubit will be in state 1, which is this state, and if there is no electron on that side, then it will go into this states. So you will need two Bloch-spheres. What do you mean by two Bloch-sphere in quantum mechanics language? They are tensor product. They are just multiplication, tensor multiplication of two states. Okay. So one qubit is to represent the upspin and the second qubit is to represent the downspin. So for example, if you want to represent this, if you want to represent this state, so I will require 1, 2, 3, 4, 4 qubits. Okay. For first site I will use 2 qubits. For second site I will use 2 qubits. And if so in the qubit language, what I will write is 0, 0, 1, 1. Okay, this is the qubit language. 0 state, 0 state, 1 and 1 state. This is how you can represent any Hubbard model state using qubits. I hope it's clear. But these are fermions, right? So only this part is not enough. This, if you recognize, is the S, the spin. If there is a J spin, so this is J plus or S plus, the ladder operator, which grows from one state to another. So if you want to go from 0 state to 1 state, that is if you want to create an electron there, right? So you need to go from 0 qubit state to 1 qubit state. So this can be done using CJ operator. In the Hubbard language, this is the CJ operator. You can simply use the S plus operator. So the qubit was, if there was no, the qubit was 0, then you can go to 1 state, right? But similarly, what you can do is the annihilation operator. The only caveat is that because they are fermions, so they have anti-commutation relation. So we know that Cj and Cj dagger and Cj are fermion operators. So because they are fermion operators, they apply they preserve the fermion statistics. So there is an anti-commutation relation. So simply using this S plus and S minus will not work. We also need to multiply using a string of Z operators. Okay, so this small thing. But even if you don't understand this, it's perfectly fine. What we are doing is we are representing the electrons, fermions, using the qubits, and we will use this XYZ, this bunch of string operators, to represent the Hubbard Hamilton. So earlier we were using CJ, C plus, C dagger and C, right? C dagger and C. We will substitute this using our Jordan linear transformation, and we will get a bunch of XYZs here. So there will be a long list of XYZs, and our H will be written without. Our state will be Bloch state on the right hand side, and we will simply multiply XYZ operators on this states. Multiplying, that's in by hand we multiply, but this is how we will do the measurement in that state. Okay, so there are
ये पॉलीमेट्रिक्स इसकी एच क्रॉस बाय 2 को 1 मान लिया है क्या इसमें?
सॉरी मुझे समझा नहीं, फिर से बोलो एक बार।
एच क्रॉस बाय 2 जो आता है पॉलीमेट्रिक्स के साथ, उसको 1 मान लिया है क्या?
अच्छा,
बस
एच क्रॉस,
बस
हाँ हाँ, यस। क्योंकि देखो हम लोग स्पीड जनरली यूज नहीं करते ना, तो कुछ
मैट्रिक्स
भी हो
वाला
सकता
पार्ट
है,
है 1 0 1
कोई भी
माइनस 1।
2 लेवल सिस्टम हो सकता है, वो जरूरी नहीं ना उसमें एच क्रॉस हो।
ठीक है।
right? So let's go to the algorithm. So this is called variational quantum eigensolver. There is also, if you open the textbook, quantum computing textbook, standard book, Michael Chuang, Chuang नाम है उसका. So if you open that textbook, there they have proposed two main algorithms, which is phase estimation and this VQE, variational quantum eigensolver. Phase estimation is for far future. If you have a very large number of qubits, okay, and it's a very nice. Someday we will discuss that algorithm. So it is very intelligent, very nice way to calculate phase of a quantum system. You can then you might remember that energy we write in e raised to I et something, right? So if you know the phase, essentially we know the energy. That was the idea. So this the phase estimation algorithm was developed theoretical, but it requires a large number of qubits, million qubits, which are precise. Then you can use phase estimation in the future. For now, what we have is variational quantum eigensolver, which is taking the measurement, but we will split the work. So how we will split the work? We will prepare the state, okay. Then we will apply a bunch of gates on this state to go into the new states, right? So what we will have is we have a list of states, list of how should I say, list of qubits, yeah, tensor product of qubits, right? We will represent our Hubbard state by list of this state, and we'll apply a rotation operator, general rotation operator, which will rotate all the qubits. So that is why I'm using theta as the representation, right? So it will rotate all the qubits and essentially it will go into new states. Now why U is used? Because it is unitary. So the amplitude is not changing, it is unitary. So it is like we are doing a new unitary rotations on each of the qubits and we are going into new states. So this is done by using qubits on the qubits, and energy we will get by averaging out, by doing a large number of measurements. This all will be done using quantum part. Some qubits we will reserve, which you can use classical bits to change the parameter. Now I'm using a word parameter. Why I'm using a word parameter, I will explain later. But essentially what we'll do is this u theta which we are writing. So there are you can say theta 1, theta 2. These are all parameters, right? Which change the system. So if you change the parameter, then you are essentially changing the state and you are going into new state. And when you go into new state, you perform the measurements and you again get a new energy. Now if the energy is lower than the previous initial state, then you are going in the right direction, right? Now this sounds very nice, but the problem is we don't know, right? Or how to know if we are going in the right direction. But experimental idea is this, that you perform measurements, change the state, again perform measurements, okay. So but the real question is, from where do we start, especially in the Hubbard Hamiltonian, where the starting state, if you choose, how do we choose? If the best guess is that you delete the u term, you only take the kinetic energy term and its eigenstate as the initial states, right? And then you uh, bring in the u term and then perform an adiabatic evolution. So I will explain later this part, okay. So this is what is called ansatz, which is guess, in which we need to guess the correct initial state. Because the landscape is too large, we have a large number of possible initial states, so we need to choose one state, and then eventually we should get the ground state energy. We should land on the ground states. So the answers guess for Hubbard Hamiltonian is that you start with only HA, okay, and HA will include only the theta, and you multiply it by 1 minus S. S is a number, simple number which goes from 0 to 1. HB will include both the terms, okay, so the kinetic energy term as well as the potential energy term, and again S will go from 0 to 1. S will obviously simultaneously go from 0 to 1. As it goes from 0 to 1, if S is 0, so you have only the HA term, and if you take S is equal to 1, then S will be 1 here, this term will get deleted, and S will be 1 here, you have only the HB term. HB term will have both the Hubbard Hamiltonian terms, okay. So the answer says that you can go from HA, which is only the T term, to the whole Hamiltonian T plus U by adiabatic evolution, right? So if you remember adiabatic, I won't go into adiabatic evolution, but what we can do is take the exponential of this. If you remember the Heisenberg picture, then you can represent this Hamiltonian in a time dependent format, okay. Now in the time dependent format, it will be e raised to I the integration dth in general if the Hamiltonian is time dependent. So we are treating S as a time parameter which is time dependent, multiplied by dt. So in that sense, if you numerically adiabatically evolve, then you should essentially go to the reach the ground state, because you see, including the U term is what is hard about Hubbard model. So only in 1D we have exact solution. In 2D and 3D it is hard to get it because of that interaction term. So what their idea is to adiabatically evolve from T states to the T plus U states. Now as an example, simple example, what we can do, starting out example, we can use the Z, simple Z state, okay. HA as Z and HB as X, right? So if the initial state is Z, then if you put here S is equals to 0, then we have only Z and there is no Y. So you have an eigenstate of Z which can be 0 and 1. If you remember, 0 was on top, you are on the top of the blush pair, and then you go to one of the axes which is Y axis, which is the eigenstates of the plus 0 plus 1 by root 2, 0 plus 1 by root 2, 1 state. So you can go eigenstate from Z to Y by adiabatic evolution. Now this doesn't require real qubits, you can do it on your own computer, and you can even do it using matrix multiplication. This is what I have done just to illustrate. So HA is an operator, right? Remember that this is an operator. So it can be written as a matrix, 2 cross 2 matrix. So this is the matrix, that is why there are two what do you say, two brackets. So this is the upper part, this is the lower part, and this is the HB, as you know, X operator, right? So initial state we can choose as 1 as the ground state, and then we evolve Y unitary operator. So e raised to I h is a function of S, which is our parameter, and then you multiply by dt. So this is the discrete version. If you remember adiabatic evolution, then there is a continuous version e raised to integration. So we had integration, instead of that we will have here summation, and then you just need to multiply this operator to the initial state to go into new state. And so res is the resultant, right? H is our this is in Python language, so it will be easy to understand. This is all H. If you represent this by matrices, then you simply get a new operator H, matrix operator, and you apply on this column vector 0 1, right? This is the operation, this is the dot product, or dot, not exactly the dot product, this is the multiplication. And in Python we can use this already, it has exponential term, so we have exponential of these things, this thing multiplied by our resultant. So this is the column vector, and this is our, you can say, one single matrix which multiplies and changes this state, and you will get a new res state. So you perform a do loop or for loop. You go into the new state, you again put this, you go into the new state. Now if you take, if in this loop the steps are small, right, this n is very small, then the resultant state, the result column vector which you look at, will not be an eigenstate of the x operator. Because if you want an eigenstate of x operator, then here we should have 0 0, right? This is like a representation in what we say, because uh, psi is a complex number, right? So the, the I part is the imaginary part, so this should be 0, and here we should have 1 by root 2 and 1 by root 2. So 1 by root 2 is how much? 0.7, close to 0.7. So you do get into the ground state, but the condition is that you should have a large number of steps in between. So the uh, so this s which you take from 0 to 1, right, the division should be of more number of steps. So if you are going to 0 to 1 and you are only doing 0 to 0.25, then 0.25 to 0.5, 0.75 to 1, then there are only 4 steps. You have split the s parameter only in 5 steps, but you can split the parameter in 50 steps and you will land on this eigenstates. So this was just an example to show how to go from one Hamiltonian to another Hamiltonian using adiabatic evolution. What we wish to do is go from t operator to whole Hamiltonian t plus u. Now if you take another example, let's say HA is the z operator and HB is this some other operator, not XYZ, which has eigenvalue -5 and 4. Then for 50 steps, what do we get? We start with this one eigenstates and land on this eigenstates. And you start with this, then we land on this states, higher eigenstate with a higher eigenvalue. So this is also an illustration to show the crossover problem. What is the crossover problem? That what you might think is that if you start with the ground state of the HA, then you might land on the ground state of SB, which is not always true, right? So this crossover problem shows it, that if you take something like Z operator, start with the ground state of that operator, you perform adiabatic evolution, do the 50 steps things, but you will not land on the ground state, right? So you will go into this upper state which you were not expecting. So that is why this is emphasizing I'm emphasizing this because it shows us the power of choice. If you do not choose the correct initial state, you will never land out on the ground state. So what is the lesson here? The lesson is that the ground state of HA will not get you to the ground state of HP, which is the ground state of the whole Hamilton that we want. Now I think we have finished here, but this was Hubbard model in K-space. What is Hubbard model in K-space? This is just what you take the what you do is take the Hamiltonian and you perform the discrete Fourier transform of each of the operators C's and C diagonals, and you go into the K state, right? So if you go into the K state, what happens is the T operator becomes very easy to diagonalize, and if it becomes easy to diagonalize, then its eigenstates are only K. But interaction term is a scattering term. So if something going with K is K minus Q is annihilated, then it will be created with a momentum K up spin, and the down spin, which we start with if you annihilate with K plus Q, then you go into the K down state. So this is event of Feynman diagram here, and you can show that this one electron is coming from here, another electron is coming from here, and they are exchanging a Q photon, and they are getting repelled. So this becomes a scattering term, right? And in general we cannot solve this term. Now if you take scattering example of our QM2 normal scattering between one electron and something another which you don't know, electron. So in that scattering, this term is always treated as perturbation. So the whole of QFT, where the scattering which they do in the let's say what is called in LHC, right? It's called LHC, right? So in LHC they do scattering. What they take is some bound states or some atom or another electron they take on this side, and some unknown potential basically V, and then you start with a K free electron eigenstates, which can be this K states but free electron, and then it will go into a new K state by scattering. Now it will go into the new eigenstates of HA only if this scattering term is small compared to this term, kinetic energy term, and that is where the calculation and experiment will meet in the scattering experiments. And so यहाँ तक they can do analytically, they can solve only if this U term is small. In solids where we know that interaction is happening strongly compared to the movement, this scattering theories do not work. Scattering theories do not work means if you open the last chapters of Griffith where they calculate scattering cross sections, then you in that they show that the scattering cross section experimentally obtained can be modeled by using some potential, but it is, remember that it is just perturbation. That is why we can't use those techniques to solve this. That is why you can't use QFT techniques to solve this problem. That hence we are using, we are trying to do is we are doing experiment. So we will represent this Hamiltonian using qubits, and then we will apply we'll prepare the state eigenstates, initial eigenstates, and initial state is where the problem is, you see. So if you want, you can start with this, you start with only this eigenstates of K, right? But It does not guarantee that your initial state will always land on the ground state. So it is more about experiment. So another thing which I've seen is that you take this sphere. Okay, now we have Hubbard model. We want to solve Hubbard model, and we have this sphere, and we have 2n. If there are n number of sides, then we have 2n number of these spheres, right? On each side there is two sphere. Right? What you do is you randomly start with any state. So here you can use two random numbers, right? And you can start with any one point on this sphere, then take another sphere. Uh, you generate random number out for it. So you start with a completely random state, calculate energy, then again go to random state, then calculate energy, and this is how wild you need to go. You see, you understand the problem, and we don't know what will happen in between. There can be crossovers like this, which can create problems. In the crossover also, what I have heard, that if this uh, initial state n equal to 50 number of this division, if you do a large number of division, so what you might be thinking that, okay, for small division it is not working, let's do very large division. What happens in states where there is crossovers is that as you go closer to this gap, okay, so essentially the gap is closing, right? So if the gap is closing, then this number of steps that you need to go, they both are in inverse of each other, right? So if they are in inverse of each other, then you need an exponentially large number of steps to reach the gapless state, and then you can't go move forward. See, adiabatic evolution only works if you have this discrete states and the gaps are not closing in between, right? If somewhere in between gaps are closing, then adiabatic evolution will not work. So this is where I'm stuck. I'm stuck at what choice should I make of the initial state. I can't use these states as the initial states. I must take, maybe a linear combination would be a much better choice. You take a linear combination of eigenstates, and hence start with it, measure the energy, and who knows, you can land on it. So I think I'll stop here. If you have any question, you can ask.